Namaskar and welcome to this series of lectures on principles of construction management. And in this lecture today, we will talk about uncertainties in duration of activities using the PERT in scheduling. So far, what we have said is that the time of completion of an activity is firm, that is, it's a given number. And then we have constructed networks to determine project completion times based on interdependencies. So you would recall that in a first example, when we said there was 500 man days involved, then we divided this by 10, which was the number of people, and came up with 50 days of activity time. And then we have also constructed in the last class a slightly different network, a more elaborate network, and illustrated the concept of critical path. That is that path which needs to be monitored more regularly, more continuously than the others, and no slippage can be allowed. But in any case, when the interdependencies were taken into account, the time associated was taken to be firm. An activity ij, it was known that this will be completed in a time of tij. Now today, what we will do is, we will take a slightly different look at the activity duration. That is this Tij, with the emphasis of incorporating the element of uncertainty. How do you incorporate a situation when the Tij is not a firm number but more like a probability distribution? An activity may be completed in 10 days, but it might spill over to 12 days. If something good happens, if we are lucky, then it might be completed in just 5 to 6 days. So this idea that the time associated with each activity is not necessarily a fixed number, that is something which we will focus on today in our discussion. So how do we actually go about estimating the times for the different activities? One simple approach is to keep records that will give us the average durations. So a construction company keeps a record for erection of trusses and so on, and finds out that, okay, in different projects, what is the kind of time that it takes. And from there, we try to find out the productivities and then try to map that into a new project and try to estimate the time involved for that project. We have talked about in the initial part of this course that each construction project is really unique. So the bridge built at a particular place is surely different from maybe a similar bridge but built elsewhere. Also, the productivity of labor during the course of the project changes, and that could also affect the duration of activities. So if there is an activity, you put a gang of labor or a certain set of workers, on day one, they may not be able to produce the maximum output. But as they learn the activity, as they learn their role in the whole process, their productivity improves. So how do we keep track of these kind of things? Going back to the basics, usually the duration Dij of an activity is determined using this formula, which is Aij upon Pij multiplied by Nij, where Ij is the activity that we are talking about. Aij is the required amount of work, Pij is the productivity of the person, which could possibly take care of the learning curve and so on, and Nij is the number of persons working on that job independently and together. So with this, we can find out the Dij. But each of these parameters has their own variations. For example, as far as Aij is concerned, the only estimate which we can make from is the good for construction drawings. It might happen that there will be some changes in the total amount of work at site. Whether it is paid for or not, it doesn't matter, but the fact is that if additional work is carried out or less work is carried out, then it will affect the time duration. So coming to the next part, which is labor productivity, this could also be an important aspect of determining the total time involved, and that is where the learning curve becomes important. So what is the learning curve? A general understanding of the productivity rates can be obtained from the concept of learning curve, and the basis of the learning curve lies in the fact that as crew becomes familiar with the activity and the work habits, their productivity tends to improve. Of course, there is a limit beyond which it does not improve. There is a limit to the capacity of each worker. This capacity may be different for different workers, But sure enough, there is a starting point and it goes through a learning phase and a steady phase for each worker. In other words, productivity increases as the crew gains experience, which is possible if sufficient time is available. And in most construction projects, that is indeed typically the case. So now, another thing is the number of workers. This equation here assumes that the duration of an activity is inversely proportional to the number of persons in the crew or the number of workers in the team. But is this assumption absolutely true? Is it true in the absolute sense? If we keep increasing this Nij, is there no limit for the reduction in the duration that we get? There are two reasons why this assumption is not really true. One is the crew may not be able to work independently. In a certain construction site, there is a limit to the number of workers who can be accommodated without interfering with each other's productivity. So that's one part of it. The second thing is coordination between individual tasks has to be ensured, and that also becomes difficult. We all know the saying that too many cooks spoil the broth. So if there are too many people trying to do an activity, that also has an adverse effect on the time duration. Apart from the workers working independently, the coordination between individual tasks and the individual crew members has to be ensured. More persons in the crew may result in the delay in the following situations. An example is design tasks are often divided between architects and engineers, in which greater coordination is required among themselves. In such situations, more the number of people in the crew will obviously affect the coordination, and therefore it affects the time. Ensuring a smooth flow of material or information of any nature may become increasingly difficult if there is more number of people in the crew. Further, in projects which are being executed for the first time, it may not be possible for planners to finalize the exact estimates of the parameters like productivity rates, optimum number of people in the crew. Other considerations may include practical difficulties like the weather, contractors' failure to deliver materials, machinery breakdowns, and so on. Also, most of the activities that are outside the control of the client are certainly uncertain. One simple example could be the time required to get approvals from outside agencies, and that could affect the project in different ways. What this competent authority means is, for example, if there is a project which requires an approval from a pollution control board and such regulatory authorities, that might be not within the control or within the powers of the client to be able to implement. And that introduces an element of uncertainty as far as the completion of the project is concerned. And it's not only the project, but also it has the effect obviously on individual activities, and those individual activities in turn affect the project. This underlines the need to understand that there exists an uncertainty in estimating activity duration, and therefore considering to use continuous probability distribution functions becomes relevant in this case. So what we are saying in this sentence is, instead of assigning a particular time t for any activity, can we not talk in terms of a probability distribution? That is, yes, this activity will take some time, but that time could be maybe a little less, maybe a little more. So whether this distribution should be normal or not is the next question that we need to answer. So without going into the statistics of the whole issue, let's try to understand the basic story of the normal distribution. The normal distribution with values widely spread away from the average is the situation where the standard deviation is high. Compared to this picture here is a situation where the peak is sharper, which means that the area in this part is closer to the mean. If we want to go to the same area here, we will go more standard deviations away from the mean. However, in both cases, the normal distribution is symmetric. So the problem with our construction activities is that they are not necessarily symmetrically distributed. So now, what are the requirements that we need to impose in determining or finding the kind of distribution that helps us say that yes, this is what really meets our requirements? The probability of reaching the most optimistic time, which is early completion, should be very less. So this is the situation where we become lucky and we are able to achieve the target very quickly. The probability of reaching the most pessimistic time should be very less. That is, there should be a time where we will definitely be able to complete the project under most adverse conditions. Then there exists only one most likely time which would be free to move between these two extreme conditions. So what we are saying is that there is an optimistic time T naught and there is a pessimistic time Tp. Between this T naught and Tp, we want to define a distribution which is not normal. So either this most likely time will move towards the left, in which case the pessimistic time becomes an outlier, or it will move towards the right, in which case the optimistic time becomes an outlier. So this amount of uncertainty should also be measurable. So once we understand these requirements, we find that the beta distribution that is used in statistics satisfies these requirements for us. So we can use the properties of the beta distribution and move forward as far as determining the expected times of the activities and so on is concerned. So now what is a beta distribution? We assume that this is the most likely time, this is the pessimistic time, and this is the optimistic time, and this distribution is skewed to the right. In this case, however, on the figure on the right, for the most likely time, the distribution is skewed to the left. So this is a situation where most of the times we will be able to complete the project here, except if we become very lucky, we might hit the jackpot and come somewhere here. In this case, we will probably be able to complete the project somewhere here, and only if we are not running in luck at all, we will be able to complete the project within the pessimistic time. So this is the kind of thought process, and we move forward and try to see how the uncertainty in estimating activity times can now be incorporated in a scheduling process like PERT. PERT is the Program Evaluation and Review Technique, and the uncertainty in estimating the duration of an activity is considered in this technique as against the critical path method that we saw in the last class, where the activities had a firm time of completion. It's more suitable to control jobs that have not been done before and there is more uncertainty in the activities. PERT assumes the three estimates of time are random variables satisfying a beta distribution function. So this is what we have been talking about, and now let's try to see how we actually implement it on ground as far as activities are concerned. So we have been talking of an activity ij all the time. So here also we are saying that there's an activity I and j, and we are talking of 3 times associated with it. Optimistic time TO, which is the shortest possible time of completing the activity under ideal conditions. The most likely time Tm, which is the best guess of the time required to complete the activity, and the pessimistic time Tp, which is the maximum time required to complete this activity. So usually the notation followed is given here. For an activity ij, we give To, Tp and Tm. Now from here, the expected time for completion and the standard deviation in the activity. We know the To, Tp and Tm, then how do we calculate the T expected of the activity or for the activity ij? Now this is calculated using this equation, that is To plus Tp plus 4 times Tm divided by 6. So I am not getting into the derivation of this. What it really says is that these are the pessimistic and optimistic times, and we are giving a higher weightage to the most likely time, and we are getting an estimate of the time at which or during which this activity will be completed. Please remember that this expected time does not mean or does not give you an idea of the 50% time of completion. This time does not mean that the activity will be completed 50% of the time. That would happen if the time of completion of that activity was normally distributed. Given that it is not normally distributed, Te does not conform to a 50% probability of completion of that activity. Continuing, the variance, that is St square, associated in estimating the expected time of the activity is evaluated as Tp minus T naught divided by 6 squared, and then we must reiterate that TE is taken as a random variable. Moving forward, let's try to implement this thought process in an example. Let's talk of 4 activities A, B, C and D, and if these were the times that we used in a CPM calculation, that is the firm times. Now this table here, or this part of the table here, gives you the TO, TP and the TM for these activities, and the way these TO, TP and TM have been chosen is to ensure that the time in CPM and the expected time of the activity are taken to be the same. So activity A has 10 here, it is TE here, it is 8 here and 8 here, 15 here, 15 here and 12 and 12. So this effectively ensures that the TE is the same. Similarly, using this equation here, we have calculated the ST associated with each of these activities. So if we examine this table closely, we find that for activity A, this T0 is a little bit of an outlier. These two times are fairly close to each other, but T0 is the optimistic time. In the case of B, this number here, that is the pessimistic time, is the outlier, and for activity C again, this is the outlier and this is the outlier here. So what we have tried to do through this arrangement of numbers is to convey to you that these activities are not normally distributed, and sometimes they are skewed to the left or they are skewed to the right. And we've already talked before that skewing to the left and skewing to the right has a different meaning when it comes to interpreting the time duration associated with an activity. So now let's actually consider some numbers. Let's consider a network that has 2 activities A and B as shown here. The 3 estimates for the durations of these activities in days is given on the arrow. So here is the TO, TM and TP for activity A, which is 1, 2, and TO, TM and TP for activity B are 6, 14 and 16, which is 2, 3, that is the activity B. So what we are required to do is to compute the total project duration using the concept of expected times of activities as we have defined earlier, and compute the project durations in the following cases. If the activities are started on their respective optimistic dates, pessimistic dates and the most likely dates, and then of course we can discuss those results a little bit. So working out the TE and the standard deviations, we find that for activities A and B, we convert this information to this table here. So using these formulae, we calculate the expected times of completion of the activities and the variances. So the total project duration considering the expected time of the activities is 23, that is 10 and 13. Now coming to the second part of the problem, which was to say that, well, if activities are completed at the optimistic times, then of course if we go back to our representation on the time axis and try to say that A is completed in 4 days, then B can immediately follow from here, and in 10 days the project will be over. However, if they start at the pessimistic dates, the project will be over only in 28 days, that is, this will take 12 days and then this will go on for 16 days. As far as the most likely dates are concerned, then we are talking of 11 and 14, which is giving us a number of 25. So the project duration obtained by considering the most likely times of activities is 25, is very close to the results obtained by the expected times, that is 23, that is this number here. The time to complete the project if activities started on their pessimistic date, that is 28 days, is also pretty close to this result. So this is 28 and this is also close to this result of 25. However, the project being completed in these 2 dates, the fact that both of these were outliers only shows that the project can be completed, yes, in 10 days, but we understand that the probability of being able to complete this project in that time is indeed very low. So in the most simple terms, what we are saying is that we become lucky not only once but twice. Not only the activity A is completed in the optimistic time, but activity B is also completed in optimistic times. So we all know the basic probability kind of questions, that A and B has to happen in this case. We have to have A being completed in its optimistic time, and we have to have B also being completed in its optimistic time. Of course, there are other combinations that A is completed in its optimistic time and B in its pessimistic time and so on. So that is the kind of range in the time estimation that is important, or that becomes relevant as far as construction management is concerned. So continuing our discussion further, how do we determine the critical path in this method? The critical path is determined by carrying out the forward and backward pass of activities with durations being taken as the expected time of completion. So of course, we take the expected time of completion and then we use probability concepts to find out what are the probability of completing the project in that time and so on. So expected length or duration of the project, capital TE, is calculated by summing up the expected durations, small TEs, of activities on the critical path. So what we are saying is that if we say that this is the critical path, we are not denying that there are no other paths. There can be other paths, but this is the critical path. So for this critical path, we take the activities on this path and try to find out the expected time of the project using only the expected times of the activities on the critical path. These activities which are non-critical will have to be dealt with separately. And the variance associated with the critical path is the sum of the variances of the activities on the critical path, and we can find out the standard deviation by finding the square root of this variance. So this is the statistical concept which we are not deriving in this course, and I am leaving it to you to take a look at some of the statistics textbooks and move forward. Now, since the capital TE is the sum of small TEs, it is indeed a random variable and follows normal distribution according to the central limit theorem of statistics. The fact that capital TE follows normal distribution can now be used to do these two things. Find the probability of completing the project within a target duration. If there are two activities, we can ask the question that, well, there are some times associated with these two activities, but what is the probability that this project will be completed within a certain time, whatever that number is? That we will see as an example later on, but also we can find the expected completion time with a given probability. Basically, these two questions are just two sides of the same coin. Correspondingly, the standard normal deviate Z is evaluated as TD minus TE upon ST, and this is something which comes in very handy when we are trying to answer questions such as these. So now, to use an illustrative example for PERT, let's say that there is a network which is given here, which is a part of a larger network. So there is a lot of activities here and here, but we are talking only of this part because that is what is our critical path. So for this critical path, the durations are given here for the activities A, B and C. This is the TO, TM and TP for all these activities. So what we are trying to find out is the total project duration and the probability of completing this project within 17 weeks. Now 17 weeks, please see, is, if we do a very simple calculation, 4, 4.5 and 6 will give us 14.5. So what we are saying is that if we just take the most likely times, we did that in an example just now, that if we just take the most likely times, it turns out to be 14.5. So what we are talking about is that what is the probability associated with completing this project, not in 14.5 or 15 weeks, but in 17 weeks. So what the probability should be is what we need to calculate. So moving forward, we first calculate the TEs and the ST squares using this formula, and we find out the capital TE, which is the total project duration, by summing up these three small TEs, and we find 15. Similarly, the variance which is associated with the project is the sum of the variance of the activities, which is 1 in this case. So the standard deviation is 1. So we have this calculation carried out. Now with this calculation, we go to the charts and tables relating to finding out how this area is related to the number of standard deviations that you go away from the mean. So if you do this exercise for this particular project, here we have 15, here we have 17, and here we have 1. 17 is our target. We want to find out what is the probability associated with completing the project in 17 days, which is higher than 15, which is the most likely time of completing this project. So this number here, which has been arrived at using the expected times, is 15, and we are trying to find out what is the probability associated with completing the project in 17, and this is the standard deviation. So the Z value is 2, and with this, if we calculate the required probability, we will find that the answer is 97.7%. So what we can say is that the probability of completing this project in 17 weeks is 97.7%. Here we can say that yes, the capital TE represents that time which has a 50% probability of completion. So with this, we have introduced the concept of PERT, we have introduced the concept of uncertainty in the activity durations. Now suppose instead of 17, we were talking of 13. If you go back to the data given here, the T naught for the 3 activities is 3, 4 and 4. So the idea is that instead of 15, which represents the 50% probability of completion, we are talking of going -2 here at 13. So what will be the probability of completing this project in 13 days? Of course, there is a finite possibility because the optimistic times associated with these 3 activities is indeed less than 13. This is something which I am leaving to you as a food for thought. You try to do this example on your own, and I am sure you will get the answer very quickly. And I hope that you now understand how to handle these concepts and be able to calculate or estimate project durations, find out the probabilities associated with completing a project in a given time, and so on. With this, we'll just give you the list of references, which I always do at the end of a lecture, and look forward to seeing you again. Thank you.